And you use certain graph to take these. So this one is kind of period. Step, sample, you take this, you take sample. And then for period, that means the signal will repeat, right? The value will repeat, that means periodic signal. So for this cos x of n is cosine of omega naught n. For certain omega naught, they will repeat, but certain other omega naught, they will not repeat. The condition for period is that. So cosine omega naught n is periodic if and only if omega naught equal to some k over m pi for certain integer k and m. So only in this case. Okay. So that means the value can repeat. This is the case, the value can repeat. If you cannot write omega naught in this way, cannot write it as a, this is fraction, right? This is a rational number. A rational number times pi. If omega naught cannot be written in a rational number times pi. This one is not periodic. And similar, sine is also same. And we can have more, not just cosine omega naught n. Omega naught n plus some any number a. A is a kind of a phase angle, any phase angle. Same thing. All of these signals the periodic only if the frequency is k over omega, k over some f times the pi, where k and f they must be integer. So this is quite different with the continuous times case. For continuous times case, cosine of omega t plus phase angle, they will always be periodic, right? That's a continuous case. But for discrete time case, you cannot say that. Does this make sense? Makes sense because in the discrete time case, we hope the period is an integer. This is a strong restriction. One is integer. Period must be an integer. And for continuous times case, the period could be any number, right? Any number. So we have this different. All right. And then we will consider what is the period. This is periodic. This is frequency. This is frequency. This is frequency. We have this frequency, but then what is the period? What is the period? If omega 9 equal to k over m times pi, and then the period, I say n, will satisfy this one, cosine omega naught n plus n equal to omega cosine omega naught n. Right? Actually, this is a kind of definition for the period. When the time you plus that n, you will have same value. Okay? So we have this one. That capital N. That capital N have to satisfy this condition. This condition. Okay. Now I plug in the omega 9. It is omega. Cosine of omega 9 is k over m pi times this lowercase n plus k over m pi times capital N equal to cosine of k over m pi times lowercase n. For this one, we have a lot of solutions. You can imagine, right? For any for any n such that k over m pi n equal to some 2 pi, 4 pi plus or minus 4 pi, blah blah blah, all of these n will be a period. Right. All of these kind of things. All of these kind of things. So you will have a lot. Yeah? Okay, and the example is you want to find the period of cosine of any number like 7 over 11 pi, and we want to find the period of this. What's the period of? Okay, now check 7 over 11 pi. 7 over 11 pi times that capital N equal to check this one. We want to find capital N satisfy this. So I times 11 on both. So I have 7 pi N equal to plus or minus times 11. Okay, I write in this way. Times 11. Then N will be, I can just do it by one step first. From here, I can get this directly. There will be plus or minus 2 pi or plus minus 4 pi and so on. I need a times just 11 over 7 pi. Right? And a pi and pi I can cancel. This is will be plus or minus 2, plus minus 4, and so on, times 11 over 7. But n must be integer. So I can have, like this is 2, 4, you want something, can cancel with this 7. You get it? You want integer, right? You want integer. Like 2 times 11 over 7, this is not integer. But you can find, this is not, up here, plus or minus 14, and plus minus 2 of it, 48, plus or minus 3 of it, this is 3, 42. This one times 11 over 7, right? Okay, then 7 cancel. So I don't need this, I start from here. This is a positive, negative. 14 over 7, I get 2, so I have 22. And then 28, I have 3 of it. I have 4 of it. 4, 7 is 28, 4. So 44. And next will be, this will be 6, right? 6. Okay, all of these, they are periods. And basically, this is a period. So, n equal to 22 is a period. Is one of the period. It is a period. We know the period. The double is still a period, right? So here, 22 is a period. 44 is also a period. 6 is also a period. We have all periods. And actually, here you also know, like. This one, 2 pi means 1 cycle in a continuous state. 4 pi means 2 cycles in continuous state. This, I use 14, that means 7 cycles in a continuous state. Now this one, this signal, it is a period that it have to go over 7 cycles in continuous sense. You get 1 period in 3 times. Because you take sample. Just in 1 cycle, the samples will not repeat. 2 cycles will not repeat. Until you go 7 cycles, okay, you will go back. Make sense? Do you remember the example last time I showed you? That example, you need 3 cycles in continuous case. You can have a discrete time period. Right? So in the MATLAB. But in MATLAB, you can just look at it. Let computer do it, then you find, oh, it looks like that. Now we have the way. You can solve to find it. Understand? Do you understand how to do it? Yeah. You want to find the period of it? You check. You replace this lowercase m by capital N. You want them to be that period, 2 pi, 4 pi, and so on. And then try to solve it to find those integer n's. Then you get the period. Alright, this is the one thing different. And the second thing different is still with the 2 pi, related with the 2 pi. I will say if x of n equal to cosine, I use cosine omega naught n plus just omega naught n, then we will have the x of n equal to cosine of omega 0 plus 2 pi times n. Am I good? And then write this. If xn use omega naught as a period, is a cosine of omega n. Then I add 2 pi on the frequency. I have, okay, it looks different, right? But actually they are same, right? Can I have these? Equals 2 pi. If you allow, you can check. You just multiply these inside the omega naught plus 2 pi times n. Okay, cosine, here you plus 2 pi and you get same thing. This is the factorization omega 0. Okay, yes. So for the frequency, omega naught and omega naught plus 2 pi, we know they are frequency, right? You put omega naught here is the frequency, right? For cosine signal, this is the frequency. This is also frequency. These two frequencies, they are same. Does it make sense? Yes.
You have it as not equal to.
Do
you mean equal to?
Right, they're equal to, right? You said the values are same.
Yeah.
Yeah, the values are same. But in a continuous time signal, a frequency you plus 2 pi or plus anything, you will have different frequency. Am I right? So continuous case. In continuous case, the frequency you have 1, then 2, then you plus 2 pi, you plus 4 pi, you can have frequency even higher and higher and higher to infinity, right? But for continuous case, you plus 2 pi, you go back. So you plus 2 pi in frequency, that means you do nothing. So this is quite different for continuous case. And discrete time case, these two are different. So I will say frequency omega naught and omega naught plus 2 pi, they are same. This is in the discrete case. For continuous cases, they are different. This is high frequency, right? You plus some numbers, 2 pi or even any number, you plus on it, you have high frequency. This one, in discrete time case, you get same. Does it make sense? Yeah, I will show you in the MATLAB video. Now let me give you results. So we can restrict the period, the frequency in range, in region from negative pi to positive pi. From negative pi to positive pi. If you have frequency like pi plus 0.0 pi, or just pi plus 0 to 1, that is you see example. Frequency pi plus 0.1 equal to pi plus 0.1 minus 2 pi, right? A plus 2 pi, you get same thing. You minus 2 pi also same thing. So this is what? This is a negative pi plus 0.1. So negative pi, and plus 0.1. And this is a negative pi, here's a negative 1. This one, and this one. So for frequency, we'll make this one and this one same frequency. Okay. So we only need the frequency between negative pi to pi. So okay. Good. Oh, okay. I touched some keys, so the screen was locked. Okay. You decided to put the control panel in the, in the place close to me. Maybe I did right in this way. Okay, you see? So the frequency in the period, in the interval from pi to 3 pi, they'll be same with from negative pi to pi. They'll be same from like here from 3 to 5 pi. So every 2 pi, this length is 2 pi, right? 2 pi, another 2 pi. We only need 2 pi. So if a frequency is here, you minus 2 pi, you go to here. You minus 2 pi, okay, finally get this one. So no matter what is frequency, if this is in the interval negative pi to pi, okay, it's good. If it is out of this interval, you need a plus or minus some 2 pi's. Then several times you will get frequency locate between negative pi to pi. Okay. Maybe in this way, negative 3 pi to negative pi. You need a plus some 2 pi to get the period. So the period, we only want the period from range negative pi to pi. We only need the frequency from negative pi to pi. This is also different between continuous time signal and discrete time signal. Now, when you consider frequency outside negative pi and 2 pi, it is kind of a repeat of the frequency from negative to positive. Negative to positive. All right. And also, we have another thing. Negative frequency and positive frequency. What's the meaning of that? Negative frequency. I say cosine negative omega n. This is we're saying with cosine omega n, right? And the sine negative omega n, there will be negative sine of omega n. Right? So for a negative frequency, for negative frequency, actually, you can say they are same thing. We say what is frequency? It is a kind of number to measure how fast, how rapidly the signal go over from positive to negative, right? Like cosine going up to 1, then lower to -1, then 1, then -1. It's change. How fast, how rapidly it change. It change fast, is high frequency. It change slow, there will be lower frequency. And the negative frequency and the positive frequency, in this sense, they are same. Like cosine and sine. Cosine, they're totally same. And sine, just change the amplitude or change the value. So positive frequency is going up and down, up firstly and down second, right? Then in negative frequency, it will be down firstly, then up, right? But the speed, the value to measure how rapidly the change positive negative, they are totally same. So you can think, okay, basically, frequency will be the number in the interval 0 to pi. 0 to pi. Alright. So for frequency, yeah. This is just for discrete time signal, not for continuous time signal. For discrete time signal, the most important is from 0 to pi. Then for the other part, like for negative side, for cosine, you get same thing with positive frequency. For sine with negative frequency, that means use positive frequency but reverse the weight to other. For positive frequency is up, the negative frequency will going down. And the positive going down, the negative frequency will going up. But the speed up and down is the same. And the cosine will be same pace, up and down and up and down. This is for cosine. All right. This is for the frequency. Okay. I think I finished the part for the sine signals. Any questions about this? Then we consider another thing is still about the operation. We consider operation last time. We have operation for signals. We have multiplication and summation of signals. We also have convolution of signals. All those operations is on the value of signals. But for a signal, a signal is like x of n. So you have x and n. X is the signal. Signal's value. And n is the times value. Right? For x of n, we have this two. Now if we have some change on that n, what do I have? Your operation is also. Okay, the first one we consider x of n minus some n0. What it is? Maybe you already know that. Time shift, yes, it's a time shift. But just in the discrete time case, so both n and n0 they will be integer. So n and n integer. So this is a time shift. Time shift. If I give graph like if this is a x of n, then this will be is n0. This is n. This is x of n. This is the x of n minus n0. So shifted by n. Shifted by n0. Shifted by n0. This form, remove this form by n0. So this is the shift. Shift by n0. And second one is x of negative n. Negative n is like you flip the time, So it's like this one. If this is x of n, then this will be like this. Right? You reverse the positive to negative, negative to positive in the end. So this is the x of negative. Same like that. And we can have more complex. 3. Okay, this is not, it's hard to give, this is not special type, that is generally. I use the example to explain. Like x of n, which is, I use like point A to the n and the u of n. Okay, this is x of n. Then we consider what is the x of, okay, like n minus 3, x of negative n. Okay, that is example of the first one. Then I really consider like this: 2n minus 4, x of 5 minus 3n. Yeah, the first one and the second one, they are one of the first type and second type of it. And the third and fourth, they are more general, just like kind of arbitrary change. And even you can consider it, for example, you use n. Anyway, we just this will be enough. Yeah, in this course this will be enough. Okay. Now what are these? X of n minus 3, there will be point A, n minus 3, u of n minus 3. If you write it as a formula, it is just like this. If you want to look at it, it will be, okay, this one we know it is this, right? This is x of n. Here's 1, here's point A, then point A squared, and q, and so on. Now the first one is shifted by 3, so here, this is 3, this is 0, 1, 2, 3. And here's 1, and for n equal to 4 is point A, and square, and q, and so on. So it looks like this, 0, 0, 0, 0. This one 0, 0. Okay. The negative n, it is a point A, this is negative n, u of negative n, right? You just replace n by negative n. Then this one will look like reverse. So in the middle is still in the middle. This is 1. But point A go to this side. And the square of it, cube of it looks like this. And for positive n, they are 0. This is this one. And x of, okay, I need these two. These two, you need to work like this. You put n. For example, you put, something. Okay, that's it. N, like I suppose, like I use negative 2, negative 1, 0, 1, 2, 3. At least this n. And then I need 2n minus 4. Okay, I check first one, 2n minus 4. So here's a 2n minus 4, then x of 2n minus 4. 2 minus 4, what it is? This is a 2n minus 4. N is negative 2. 2 of negative 2 is negative 4, minus 4 is negative 8. And this is 2 of negative 1 is negative 2, and negative 4 is negative 6. 2 of 0 minus 4. 2 of 1 that is 2. 2 minus 2. 2 minus 4 is negative 2. 2 and 4 minus 4 is 0. 2, 3, you get 6, minus 4, you get 2, cancel out. So actually this 2 minus 4 is, all the even values start from negative. Here is a negative 8, the 6, 4, 2, something. Whatever. Okay, then what is this value? This value will be x of negative 8. Okay, now you plug in the original, what is the x? X is here. X is here. So x of negative 8, you get 0. Negative 8, negative 6, you also get 0. Oh, sorry. That's 0, 0. And when, okay, when 2 and minus 4 is 0, then x of 0, x of 0, x of 0, 0, I get 1. And then here's 3, here's 2. So here will be x of 2. X of 2 will be square of it.